Okay, hello, I'm James, and I'm going to be discussing the solution to the step problem on assignment 15 of the foundation modules. So, this question, there is quite a bit going on here, right? Like, this is a fairly long question. We've got some sequence of real numbers, and they are defined recursively. So that means that the n plus 1th term is dependent on the nth term, right? And we have this formula here, where k is some arbitrary constant, and I'm going to call this formula star. Okay. Part 1 of the question says, determine the values of k for which the sequence star is, and then the first bit is constant. Okay. So, what does it mean for a sequence to be constant? So, a constant sequence. Well, in general, it means that the sort of k, or the n plus 1th term, is equal to the nth term, right? We don't need to deal with that sort of restriction. We can all we need is the second term to equal the first term, okay? That's restriction enough, right? Because that will give us a constant sequence, okay? So, a constant sequence will certainly require u2 to equal u1. Okay, well, we know that u1 is 2, so we need u2 to equal 2. Okay, well, what is u2? u2 is k minus 36 over u1, by definition. u1 is 2, so this is k minus 36 over 2, which is k minus 18, and we require this to equal 2 if the sequence is going to be constant. And so this means that k equals 20 gives a constant sequence. Okay? So that's how we do the first part. Now, to be honest with you, part B and part C are going to be very similar. Okay? It's just the algebra gets a bit more tedious, so bear with me on the algebra. Hopefully I can do it all in one go. Okay, so periodic with period 2 will require u3 to equal u1, right? Well, it doesn't require u2 to equal u1, but it will certainly require u3 to equal u1, right? So, what is u3? Well, so u2 we found was k minus 18, right? u3 is k minus 36 over u2, which is k minus 36 over k minus 18. Okay? And we require this to equal 2, because that was the condition. Multiplying this, well, basically we've got to solve this equation. So how do we solve this equation? One way we can do it is simply multiply through by k minus 18. We'll end up with k times k minus 18 minus 36 is 2 lots of k minus 18. Now let's just do the algebra. We're going to end up with k squared minus 18k minus 36 equals 2k minus 36. The minus 36 is cancelled. You end up with k squared minus 20k equals 0, which implies that k times k minus 20 has to equal 0, or in other words, k equals 0 or k equals 20. Okay? Now, one of these answers is correct, one of them is wrong. And I'll tell you that k equals 20 is wrong, and that's because we already found that k equals 20 gives us a constant sequence, okay? And so that doesn't have period 2, because period 2 means it repeats after every second term, okay? So we should definitely say, hence, k equals 0 gives a sequence with period 2, as k equals 20 gives a constant sequence. Okay? So that was part B. Part C, again, it's a similar idea, but it's just the algebra gets harder once again. So, periodic with period 4 requires u5 to equal u1. u5 to equal u1, like that. Yeah. Because we need this sort of gap of 4 before it repeats, right? So let's do this. Oh, okay. So u2 equals k minus 18, and that's easy. u3 we already found was k minus 36 over k minus 18. Yeah. u4 is k minus 36 over k minus 36 over k minus 18. Right? Now we should do some arithmetic here. Let's simplify this before calculating u5. So u4 equals, so simplifying this expression, gives us k minus 36 over. Rewriting this, so I'm going to get this bit here. Ooh, let's make sure you can actually see it. I'm going to rewrite this denominator as with the common denominator here. So I'm going to write it as k squared minus 18k minus 36 over k minus 18. Hopefully you agree with that. Evaluating this, we end up with k minus 36 times k minus 18 over k squared minus 18k minus 36, right? So just flipping the fraction. Again, getting all of this under a common denominator now gives us, so this is going to become a k cubed minus 18k squared minus 36k minus 36k plus whatever 36 times 18 is, right? And that's all over k squared minus 18k minus 36. Okay, hopefully you agree with the algebra so far. I'm just getting things under common denominators and simplifying and doing all of that, right? That's all I've done so far. Okay. u5 is equal to k minus 36 over u4, which is a bit of a nightmare, isn't it? It's k minus, so 36 over u4, so that's 36 times the reciprocal of this, right? So that's 36 times k squared minus 18k minus 36 over k cubed minus 18k squared minus 72k, right? I'm just combining the two 36s there, plus 36 times 18, right? And I require that u5 equals u1, which equals 2. Okay, so this is the equation that I need to solve. So I'm going to do that on the next page. So maybe let's write down the equation again that I'm actually wanting to solve here. So just to recap, I'm wanting to solve k minus 36 times k squared minus 18k minus 36 over k cubed minus 18k squared minus 72k plus 36 times 18 equals 2. Notice here that I haven't actually evaluated 36 times 18, right? Like I could take a couple of minutes to evaluate that if I want, but if I don't need to, then what's the point, right? I'll do that right at the end. In my opinion, it's simpler to leave it as this rather than some, horrible number. Okay, so how do we solve this equation? Well, I would multiply both sides by this cubic and then collect some like terms. So multiplying both sides by the cubic, we're going to end up with k to the 4 minus 18k cubed minus 72k squared plus 36 times 18k minus, expanding this bracket, 36k squared plus 36 times 18k plus 36 squared equals, and I'm going to have to go on to the next line here because it's not going to fit in, so 2 times this thing now is 2k cubed minus 36k squared minus 144k plus 2 lots of 36 times 18 is 36 times 36, right? Because you just multiply the 2 by the 18. So that's 36 squared So, what have we got? We've got a k to the 4. What else have we got? So we've got a k to the 4. We've got an 18. We've got a minus 18k cubed, a 2k cubed here. So subtract that off. We're going to end up with a minus 20k cubed. What have we got in terms of k squareds? We've got this minus 72k squared. And then we've got a minus 36k squared, but we've also got a minus 36k squared on the other side, so they cancel. So we're just left with a minus 72k squared. In terms of k's, what have we got? So in terms of k's, we have got 36 times 18 lots of k. So we've got a 36 squared times k minus 144, right? I think. What does that give us? Okay, I think I'm going to have to do this just off to the side here. So maybe I'll write it out in full. So we've got a 36 squared times by k plus a 144 times by k. I'll deal with that in a second. And then the 36 squareds both cancel, so that's equal to 0. Okay, so let's deal with this. What's 36 squared? I don't actually know off the top of my head. Maybe some of you do. 6 times 6 is 36. 6 times 3 is 18. Plus 3 is 21. 3 times 6 is 18. 3 times 3 is 9. Plus 1 is 10. 6, 9, 2. So that's 1296. I'm going to add a 144 onto this to get 1440. Okay, so the quartic equation that we need to solve is k to the 4 minus 20k cubed minus 72k squared plus 1440k equals 0. Okay, so we can certainly factor out a k. That's easy enough to do. So we're left with a k cubed minus 20k squared minus 72k plus 1440 equals 0. Now you might be thinking, how are we going to solve this cubic, right? Well, we need to look at our previous answer, right? So notice before that we found two solutions, right? We found that k equals 20 and k equals 0 was a solution. K equals 0 was the right one because k equals 20 was constant, right? Because a periodic sequence with period 2, this condition does technically give you a constant sequence. And so likewise, we would expect a sequence which is periodic with period 4, which has this condition, to also have k equals 20 as a solution, because a constant sequence does also satisfy this condition. Okay, so we would expect k equals 20 to be a solution. So from before, we would expect k equals 20 to be a solution, and so by the factor theorem, k minus 20 is a factor. Okay, so we found one factor. We're now going to carry out polynomial division. There are a few ways to do polynomial division. Again, whichever method that you've been taught or which you prefer, use that one. I'm personally a fan of the sort of grid method. It's a bit, I don't know. It's okay, I quite like it, but there are more traditional ways of doing this rather than this method, but this is the one that I use. So we're dividing by k minus 20. We want a k cubed term, so that requires this to be a k squared, this to be a minus 20k squared. We do actually want minus 20k squared, so we want another 0k squared added onto that. So that's 0k, that's 0k. But we don't want 0k, I want minus 72k, so this should be a minus 72k. That requires that to be a minus 72. minus 72 times 20, well 72 times 10 is 720, times by 2 is 1440, which is what we were after. Okay, and so we can factorize it. So I should say, so we need to solve the following. K times, and then instead of this cubic, I factorize this cubic as k minus 20 times k squared minus 72 equals 0. Okay, so k equals 0, k equals 20, or k equals plus or minus 6 root 2. Are there any restrictions on k? Like, does k have to be positive or anything? No, it just says k is a constant, and so hence for a periodic sequence with period 4, we require k to equal plus or minus 6 root 2, as k equals 20 gives a constant solution, gives a constant sequence, and k equals 0 gives a sequence of period 2, which is not what we're looking for either. Okay, cool. So, that is that part of the question. That was very tedious algebra, to be honest. But oh well. The next part of the question, then, part 2, says, in the case that k equals 37 in this solution, show that un is greater than or equal to 2 for all n. Remember n, because it's denoting a sequence, n is implicitly a natural number here. And then given... Okay, we'll do the next part in a second. So, in the case that k equals 37, show that un is always greater than or equal to 2. So, I'll say, okay, when k equals 37, what does our recurrence relation become? It becomes un plus 1 is 37 minus 36 over un. So, we'll write that down. That's un plus 1 is 37 minus 36 over un. We need to prove this by induction, right? That's how I would probably do it. So let's proceed by induction. So maybe I'll say, yeah, so let P of n, this is how I do induction, by the way, let P of n be the proposition that un plus 1 is, actually that's not the proposition, is it? That un is greater than or equal to 2. Okay, that's the proposition. Base case. Well, what do we know about our sequence here? We know that u1 equals 2. So I suppose I should say I'm proving this statement for n greater than or equal to 1. So base case, p of 1 equals 2. So p of 1, u1 equals 2, and that's clearly greater than or equal to 2, right? So p1 is true, fairly trivially. So p of 1 is true. Let's assume that p of k is true. So in other words, I'm going to assume that uk is greater than or equal to 2. And our aim is to show that uk plus 1, which equals this thing, is greater than or equal to 2. Okay. How would I do that? Well, okay, so I'll show you how I did this originally, okay? So what I'd do is I would start with our thing that we want to prove. I want to prove that this is true. And then I would sort of think about what that means, effectively. So, what does it mean? Well, how do I want to write this? Actually, no, I don't think I would do it like that. I would start with this thing, actually, and then just try and manipulate it into this form. Okay, I'll just try and manipulate it into this form. So, for example, I know I want a over UK, right? Like I know I want something 1 over UK, so maybe that's where I would start. So, UK is greater than or equal to 2 is equivalent to saying that 1 over UK is less than or equal to a half. I know I'm aiming for a 36 over UK, so it seems reasonable to multiply both sides by 36. So we know that 36 over UK is less than or equal to 18. I actually want a minus 36 over UK here, so it seems reasonable to multiply both sides by minus 1. Remembering to flip the inequality sign when I do that. And I want to add 37 to both sides. So you end up with 37 minus 36 over UK. What's 37 minus 18? That is 19. So this expression on the left here is exactly UK plus 1. So UK plus 1 is greater than or equal to 19, and that's certainly greater than or equal to 2. And so P of K plus 1 is true. Okay? So that's, I probably should say, by induction, P of N is true for all N greater than or equal to 1. Okay? The question's still not finished, we're still going. The last part of the question says, given that in this case the sequence star converges to a limit L, find the value of L. Well, in the limit, as n tends to infinity, un plus 1 equals un. That's basically what it means to say that the sequence is converging to a limit, right? Like the difference between these terms is unchanging, right? So they're both equal to some limit, call it L. And then we just substitute that into our original definition for the sequence, so which is given as this thing here, right? This un plus 1 is 37 minus 36 over un. Well, in the limit, un plus 1 equals un equals something, let's call it L, and so we end up with L equals 37 minus 36 over L. We now have to solve this quadratic equation. We seem to be doing that a lot in this question. That's L squared is 37L minus 36, right? So that's the same as L squared minus 37L plus 36 equals 0. Factorising, we end up with L minus 36 times L minus 1 equals 0, which is equivalent to saying that L is 1 or L equals 36. And then we need to just write a concluding statement, which I'm hoping I can fit on the bottom of this page here. Hence, what was the wording of the question? The wording said, okay, it converges to a limit L. Hence, the sequence star converges to, well, we need to pick one. It's either going to converge to 1 or 36. It's not going to converge to both. It converges to 36 because we know that un is greater than or equal to 2, so cannot converge to 1. Okay? So, as we just proved by induction, right, we know the sequence is always bigger than or equal to 2, so it's not going to be possible for the sequence to converge to 1, so it must converge to 36. Okay, so that was that question. It's quite a long question. It took me quite a while to do this one, right? Like 25 minutes or something. There's lots of parts, there's lots of algebra to mess up on. I do genuinely think this is a bit of a tricky question, and one that in an exam maybe I would be cautious of because of this lengthy algebra. But at the end of the day, it is just algebra, so if you are confident with that sort of thing, maybe this is a very nice question for you. Okay, thank you. Hope you enjoyed.